that the population mean is equal to a number. Okay, so that would be saying like the mean decrease in the cholesterol level is 15. And the alternative would have been more than 15. Okay, so the mean decrease, okay, so mu was more than 15. Okay, and that would be the claim. And then what we would have done was we would have collected our evidence, calculate our test statistic, and then make our decision. Okay, so now we're going to look at now we're interested in comparing the decrease in cholesterol levels between two groups of people. The first group, called the treatment group, will take the cholesterol drug, and the second group, called the control group, will take the placebo pill. Okay, placebo is like a sugar pill which has no effect because it's not putting anything into your system. Okay, there is still data of the form before and after for each individual in each group. But now we may compare the mean change in cholesterol levels in each sample group to make an inference for the population. Does taking the cholesterol pill result in a larger decrease in mean cholesterol levels than those taking the placebo pill? Okay, so now we're going to look at is the decrease in cholesterol level greater than a certain amount? We want to know those that take the pill, do they have a larger decrease than those not taking the pill? Okay, or taking the placebo pill. Okay, so you need to understand the difference in those two types of questions. Comparing the population mean to a number compared to the difference being comparing now one population mean to another population mean. Okay, so now that's looking at is the mean for one group greater than the mean for another group. Okay, where this is the pill group versus the placebo group. Okay, or the drug group compared to placebo. Okay, so now we're going to collect our data. Okay, so just suppose the following data is collected from the medical experiment in which a hospital had identified patients classified as having high cholesterol. Okay, so this might be hundreds or thousands of patients. They take a simple random sample of 90 individuals from that population, and they're given the cholesterol drug. Their mean decrease in cholesterol levels was 18 units with a standard deviation of 5.8. Okay, so there's your X bar 1 is 18, and your S sub 1 is 5.8. At the same time, so from that same population of those having high cholesterol, another simple random sample of 75 individuals was taken from the group, and their mean decrease in cholesterol levels was 6 units with a standard deviation of 4.6 units. So construct a 99% confidence interval for the population mean difference in the decrease in cholesterol levels between the two groups. So the population mean difference, that's mu1 minus mu2. Okay, we're doing a confidence interval, which tells you what formula you're going to use. So again, the formula from the very first page, our confidence interval formula for the difference in means, in population means. Okay, so when you substitute those values in, again, for the sake of time, because we're getting long on time here, X bar 1 minus X bar 2 is 18 minus 6, plus or minus 2.660. Okay, that is your T star value coming from, well, there was 75 in one group, 90 in the other. So your degrees of freedom is 74. So when you look that up, 74 degrees of freedom on a 99% confidence interval. Okay, so here's 99% right here. If you scroll down, well, 74 degrees of freedom. Notice we skip over that. Okay, so we're going to go back to 60 because that's a larger t-score, which means it allows a little more error. So 2.660. Okay, that's where that's coming from. And we end up with a margin of error of 2.15. And again, do this in your calculator to make sure you get those numbers. Okay, so we are 99% confidence that our interval, 9.85 to 14.15, will contain the true value of mu1 minus mu2. Now there, we see they're both positive. So kind of interpreting that interval, okay, it looks like that the mu1 minus mu2 came from x bar 1 minus x bar 2. Okay, that's where the positive 12 came from, and then you add or subtract the margin of error. So it's positive because that first number was positive, and it's much larger than the margin of error. So it appears that that difference is pretty significant. Okay, so it does appear, I know my writing is terrible, but it appears those who take the drug have a larger average decrease in their cholesterol levels than those who don't take the drug. Okay, so because they're both positive, okay, it does appear that those who take the drug have a larger average decrease than those who don't take the drug. Okay, if 0 was in the interval, so let's just suppose that was negative 9.85 and this was still positive 14.15, then if 0 is included in the interval, then we can't say there's a difference because 0 is in the interval, which would indicate that mu1 equals mu2. That's a realistic value, okay, or realistic outcome. Okay, but since they're both positive, that tells us that it appears that there is a difference, or a positive difference between mu1 minus mu2, which means mu1 is larger than mu2. Okay, a hypothesis test. So part B, at a 0.01 level of significance, is there evidence to support that the population mean decrease in cholesterol is greater for those who take the drug than those who don't? Well, this is a hypothesis test. So we're trying to support something. Okay, so that tells you hypothesis test. So you make your hypotheses. Okay, that mu1 equals mu2. Okay, so those that take the drug compared to the placebo. And then the alternative is that mu1 is greater than mu2, and that is our claim that the mean decrease is greater for those who take the drug than those who don't. We calculate our test statistic. Okay, so we use the values from our sample, plug into our value to get the test statistic. Okay, and again, the mu1 minus mu2, that's going to be 0. Okay, so x bar 1 minus x bar 2 will be 18 minus 6, and then minus 0. Because if mu1 equals mu2, then mu1 minus mu2 would be 0, divided by the square root of all that nice stuff. And that gives us a t-value, a critical number of 14.817, okay, which is a pretty large t-value. Now we are looking at mu1 being greater than mu2, so that means we're in the right-hand tail. And 14.817 is going to be way out to the right, but let's compare that to our critical number for t here. Okay, so t is coming from 74 degrees of freedom with at 0.01 and 1 tail. Okay, so with 0.01 in a one-sided p. Okay, so one-sided p of 0.01. Okay, with the 74 degrees of freedom, that's our 2.390 here. Okay, because we're rounding to the 60 for the degrees of freedom. Okay, so 2.390, that's where that's coming from. And we can see our test statistic is way out to the right of that, okay, which is telling us, as far as our decision for HO goes, we're going to reject HO. Okay, so if mu1 really equaled mu2, to get this result, a test statistic of 14.817 would be very unusual, which tells us that mu1 equals mu2, our assumption, was probably a faulty assumption, which means that we can support the claim. Okay, so there's enough evidence to support the claim that mu1 is greater than mu2, so it appears those who take the drug have a larger decrease in cholesterol levels than those who don't take the drug. Okay, so that's a few examples of looking at the difference in two population means. Again, the process is the same as before. It's just that we're using these formulas that are a little more complicated. But when you look at your confidence interval and hypothesis test, it's still the same idea. You take for the confidence interval, you take an estimate instead of x bar. Now we're finding an estimate of the difference of two samples. Add or subtract your t star times the standard error, and then construct your interval from that. For hypothesis test, you construct your hypotheses. Okay, mu1 equals mu2 is generally going to be your null hypotheses. And then you calculate your test statistic and then make a decision. Okay, so again, the process is still the same. It's just that you have a few different concepts and formulas going on.